So our next topic in Physics for Life Science is waves, and in particular sound waves. We now have the mathematics to analyze waves in a much more uh, quantitative way than you might have done before in Physics 11, where our analysis was necessarily fairly qualitative. So here's a function. It kind of looks like a wave pulse. But of course, wave pulses move, and this function just sits there. So how can we make it move? Well, we can replace x with something like x minus vt. And if we do that, and we let t be time, then at time 0, it's just f of x. So that's our sort of hat-like function, just centered on the origin. But if time is 1, then our function is f of x minus v. And you may know from your study of transformations in Math 11 that that just moves the whole graph over to the right. So instead of being centered on 0, it's now centered on v. And if you put in a time of 2, then it's x minus 2v. And so we see that the wave pulse is now moved over again. So, whoops, must be some more information down here. There we go. So what does that value v represent? Well, it's the distance per second that wave is shifting. But of course, in kinematics, we know that's the velocity. So this is, of course, why we use the letter v for it. Now we say velocity because we can also get direction information from that. For instance, if this is the shape of our wave pulse, a function like this, where we've taken x and replaced it with x plus 3t, that's something like x plus vt. So we know that the speed is 3 meters per second. But the other thing we know is that for an x plus a term, that it's actually shifting and moving to the left. So the difference between right and left is whether we've got plus vt or minus vt. So if you want to move right at 2 meters per second, shifting to the right, this term needs to be negative. And 2 meters per second is the speed v. So where we had x in the original function, we now put x minus 2t. And then lastly, to have it move left at 1 meter per second, shifting to the left means this is positive, and if the speed is 1, then it looks like that. So where we had x in our original function, we now have x plus t. Okay, now these are called traveling waves because these shapes actually move with time. So we have a mathematical description of a traveling wave. Now there's lots of examples in biology of traveling waves. For instance, here, this just shows that if you jump, so take a step and land on your foot, either when you're walking or running, or if you jump and land on that foot, a compressional wave travels up your skeleton. Imagine that this is your leg impacting the ground. Now, when it impacts the ground, the foot stops, but the upper body and most of the leg is still in motion. So the leg comes down a little further, and that's going to compress the bone. And that's going to lead, say, your hip joint to stop. Well, after your hip joint stops, your upper body is still moving. So that's going to compress that part of your body. And eventually, all the parts of your body will stop. But the compression travels from your feet all the way up to your neck and somewhat into your skull. Other traveling waves include, say, the pressure pulse of the heartbeat. That pressure pulse travels through the blood. The pressure fluctuation in a heartbeat also travels through all tissues and up to the surface of the skin. So we can detect a fetal heartbeat using a stethoscope. So there's lots of interesting traveling waves. We'll probably focus in quite a bit on sound. So thus far we've got a mathematical description of a traveling wave. It's some function with an x plus or minus vt term. Let's focus in momentarily on waves on a string. So this could be like plucking a guitar. We can also look at, say, the creation of sound by the human vocal cords is being described by this as well. Now, we've already dealt with this in the lab, and we know that a key variable is the linear density of the string. That's the kilograms per meter. Now, we want to derive the relationship that we used in the lab concerning wave speed. So we're going to consider a little element of string here. And the forces that act on it are the pull of the neighboring elements of string. So there's tension forces there. Now, left and right, those tension forces just cancel. In this direction, though, those two tension forces add, and they provide a centripetal force for this element of string. So we want to know what these components are. Well, we can do a little geometry here. So this whole angle here, theta, we'll just divide up into two parts, theta over 2, and we'll use a dot for that. And then this is just 1/2 of the sort of one of these triangles and one of the tension forces. We're just going to do geometry and find this angle over here. So this angle is 90, and then the tension will be tangent, i.e. will be perpendicular to the radius, so that's also 90. So this angle up here is the complement of dot, and that means that this over here must be dot as well. So that tells us that the component that we're looking for is a sine dot, i.e. a sine theta over 2 component, inwards towards the center of the circle. Now there are two of them. There'll be one tension component here and one tension component over there. So applying Newton's second law, we've got 2, and then we've got tension sine of theta over 2. That equals mass times acceleration, but the acceleration when you're going in a circle is v squared over r. Now, we're going to use the small angle approximation, which is for very small angles, sine of theta is approximately equal to theta. So where I have sine theta over 2, I'm just going to replace it with theta over 2. I'm also going to come up with an expression for the mass, because of course a mass is going to be an arc length times a linear density. Because our linear density is kilograms per meter. So when we multiply that by the kilograms, which is the length of this little piece, that's the length of an arc, that'll give us, kilograms per meter times meters gives us kilograms. But now arc length by the arc length formula is equal to the radius times the angular displacement. So for mass then, I can say it's r theta times mu. That's the arc length, that's the linear density. And then, of course, I have v squared over r. Now, simplifying this a little bit, I see that radius cancels, the 2 cancels, and the theta cancels. And we're in a position now to solve this for v, the speed of the wave on the string. So we get tension force, the tension in the string, divided by the linear density, square rooted. So that's the speed of wave on a string. A stretched string. And we use this in the lab. Now, waves will travel at constant speed down that string, so if we know how far they go, we can just do basic kinematics on that. If we have sort of a continuous wave, then we can define something known as the wavelength. It's just the length of a wave. So it's the distance between corresponding points on the wave, either, say, midpoint to midpoint, or in this case, crest to crest. That's the wavelength. Another important variable is the frequency f, and that's the number of cycles per second. Now it turns out that the wavelength and frequency are related to the speed. Just imagine the following thought experiment. Let's say we have 3 waves per second, so 3 waves each second, but each of these waves is 2 meters long. So in 1 second, you have 2 meters, 2 meters, 2 meters. You have 6 meters of wave per second. Well, of course, that's the velocity. So this suggests that the velocity of the wave is equal to the product of wavelength and frequency. If we check the units, lambda is the meters of length for a single wave, and frequency is the number of waves per second. Multiplying those together, you of course get a good unit for speed, meters per second. So which suggests that this is a good relationship. So these are basic wave properties. so I have to charge this up. Okay, now there's another way. There's some other variables that are important to describe a wave. Period is the time that it takes for one wave cycle. That's in seconds per wave. That's the reciprocal of frequency, because frequency is waves per second, period is seconds per wave. Now there's another way to measure how quickly a wave is vibrating, and that's known as the rate of vibration, and that's in radians per second. Now, since a wave is a full 2 pi radians, we can convert from frequency to period and rate of vibration using this relationship here. So as a for instance, if our frequency is 5 cycles per second, if you want to find omega, you can just think of it as a unit conversion. So we're going to take 5 cycles per second, and then a wave cycle is 2 pi radians. So in this manner, we convert to radians per second. That's really what this relationship is telling us. So we could say, or, since period is reciprocal frequency is 2 pi over omega, the rate of vibration, you could solve for omega just by cross-multiplying here. And you get 2 pi times f. So that would be 2 pi radians times the 5. Let's write that more neatly. 2 pi radians times the 5 cycles per second. And cycles is dimensionless. It's just a placeholder. So you end up with radians per second units. So either viewing it as a unit conversion or actually using the relationship, the formula, you get the same answer for the rate of vibration. Now, this is actually a Greek letter omega. It's not a W, it's an omega. And we'll see that fairly often in this course. Okay, so now we've got a relationship for traveling waves. Sorry, a mathematical description for them. We've got an expression for the speed of a wave on a string. And we've got some sort of general properties related to all waves. Now what we want is we want to have a traveling wave that repeats itself over and over and over again. That's periodic. To do that, we're going to use a particular function, not just any old function f. Instead, we're going to use sines and cosines. So we want to show that this wave does what we expect it to do, and we want to investigate what each of these values represents. Now, this function's been graphed for us already at several times. Time of 0, time of a half, and a time of 1 full second. I just use a graphing utility to do that. Now, a couple of things we can observe. First of all, we see that this distance right here is 5, and that's the amplitude. That's how much the wave is displaced from the equilibrium position, and amplitude is usually the letter A, capital A. Now, these numbers here may be familiar to you. In your previous math course, you might have called this the B number, and then the wavelength you would have said is 2 pi over the B number. Well, in physics, we don't call it the B number, we actually call it the wave number, and then the wavelength is 2 pi over the wave number. Now, if the wave number is pi over 2, 2 pi over pi over 2, according to the law of start of fractions, is actually 4. So we expect a wavelength of 4 units, and indeed that's the case, because the distance between crests here is 4 steps. So we could see that if we had a mathematical description like this, that this term here, this wave number, could be used to get the wavelength of the disturbance. Now, what about this other quantity right here, this other number? Well, it turns out that is the rate of vibration. that same variable omega we were just talking about. And it turns out the period, as we saw in that relationship, is 2 pi over the rate of vibration. Now, if the rate of vibration is pi, 2 pi over pi is 2 seconds of period. Now, what does it mean to say that the period is 2? Well, if we consider a particle here at 0, then at half a second, that particle has moved down here. It's now at the midline or 0 point. And then at 1 second, it's moved all the way down. Now it's in a trough. It's at the bottom. So that's a half cycle, right? It still needs to go all the way back up to the top. So if you're sitting at x equals 0 and waiting for a full wave cycle to pass you, then at 1 second, you're only halfway there. So we can see that 1 second is indeed a half period. So we expect a 2 second period, which is exactly what we got through this calculation. No surprise. So we can therefore identify, if we have a traveling periodic wave, you could use sines or cosines. It's going to be something like this, where there's a coefficient of x and a coefficient of t. Now, a is the amplitude. It's how far the particle gets away from equilibrium. Now, the wave number, the coefficient of x, we use a k for that in physics. Okay, and that's related to the wavelength in space. The wavelength is 2 pi over the wave number k. Lambda is 2 pi over k. Next, the rate of vibration, well, that was the letter omega. And the period of time was 2 pi over omega. Now, what we didn't do with this functional form earlier is put it in the form f of x minus vt. In order to do that, you need to factor out that pi over 2. So pulling out the pi over 2, this is just going to give us x, and this is going to be pi divided by pi over 2. It's going to be twice t. So this looks like x minus vt. We expect a speed of 2 meters per second. That means, say, that this crest here, in 1 second, we would expect it to have reached 2 meters over. And indeed it did, because at a half second it had traveled 1 meter. Then in a full second it had traveled over 2 meters. So it is indeed going 2 meters per second. That is the wave speed. So we can see that we get lots of information from this equation. We get the amplitude, the wave number, which tells us the wavelength, the rate of vibration that tells us the period, and then when we factor, we get the speed. So in general, we have to pull out the wave number, and then coefficient of time becomes the speed. But you could see as well that this speed is going to be the ratio of the rate of vibration to the wave number. So that's another relationship for wave speed. So take a second and then just practice that. Pick, say, maybe B. And for this statement, fill in this row the amplitude, wave number, wavelength, rate of vibration, period, and speed. So pause the video and give it a try now. Okay, so here's my answer. This is the amplitude, right? It's A cos kx minus omega t, plus or minus omega t. So the amplitude is 3.5. The wave number k by inspection is 2. The rate of vibration omega is minus pi half pi. We find wavelength doing 2 pi over k, so 2 pi over 2 is just pi. We find period doing 2 pi over omega. 2 pi over omega. Now, sorry, that's just pi over 2, not the minus. The minus is just telling us the direction is to the right, so that was a mistake. Get rid of that sign there. Okay, so we've got to do 2 pi over 2. That's 4 seconds of period. Now the speed, you could find that by factoring out 2, in which case you'll get pi over 4. Or you could take the ratio of omega to k. So pi over 2 divided by 2 is indeed pi over 4. This problem we'll work on in class. And the next and final thing that we will do with waves is consider a phenomenon of standing waves on a string. So we've got now this equation for traveling waves, something like cosine kx minus omega t. And if we consider the interference of two traveling waves, you can get some pretty complicated behaviors. So for instance, this might be one wave here, and then this might be another wave here. If those two waves pass through each other and interfere, well, you get some pretty complicated behavior. Right? It's just the sum of those two waves, but that's pretty complicated. An important special case, though, is two identical waves with the same amplitude, frequency, wavelength, and speed, just going in opposite directions. So here we've got a wave that's moving to the right. That's our first wave. Here we've got exactly the same wave, but now it's moving to the left. So those two waves are going to interfere with each other. Now what we're going to do is add those two to figure out what the resultant wave is. So here's the first one, here's the second one. Now it turns out there's an identity here. Cosine A plus cosine B is given by this. You can prove that identity if you really like identities. So little a is going to be this first bracket, and little b is going to be this second bracket. And we're just going to apply the identity to add these two waveforms together and see what arises when we've got these two identical waves on a string encountering each other. So the result is over here. It's going to be twice with a factor of a. Then we have one bracket, which is the sum of the two angles over 2. So it's kx minus omega t plus kx plus omega t all over 2. So the minus omega t's cancel. Kx, kx, 2kx over 2 is just kx. Okay, that's good. I'm just moving this over a bit to give myself some more room, because there's still this other term to go. So this is the cosine of the difference, so we're going to subtract these two now. Cosine kx plus omega t minus kx minus omega t all over 2. Kx minus kx disappears. Omega t minus omega t is twice omega t. Then you divide by 2, so you just get cosine of omega t. So this is what we get when we add those two waves together. And as we're going to see in class, this is a very interesting equation with an immediate physical interpretation. There's basically two parts to that, and it's going to be called a standing wave. And in class, we will then get back to what we did in the lab and start talking about nodes and antinodes and derive a nice relationship for the number of nodes that we get on a string as a function of its wavelength. But that's it for our pre-lecture video for this class.